In this section, we're going to discuss potential difference and electric fields. So it's a very visual chapter where we do want to see how we can just figure out the potential from a map of the electric field. So the first thing we're going to tackle is equipotential lines. These are very fun, I think, because they're very similar and they remind me of topological maps or contour maps for mountains and things. So we're already familiar with electric field lines and they help us to visualize an electric field. But what equipotential lines do, which are analogous to contour lines on a map, they help define where the potential is exactly the same. So on a map or on a geographical map, you would see these contour lines and they would indicate all of those points on that line are at the same altitude or at the same height. With an equipotential line, it's the exact same idea. It just shows you where all of the potentials are identical to each other. So if I have a positive charge here, I have my electric field lines radiating out, and these blue circles are equipotential lines. So that means at every single point on this circle, the potential is exactly the same. So the other thing we want to figure out is what do we notice about where the equipotential lines are closer? As the equipotential lines get closer and closer, it means that the field is going to be stronger. Just like if you take a look at a contour map, if you see a bunch of lines getting closer and closer together, you're reaching the peak of the mountain and there's a greater slope or gradient. Very similar in this case. As you get closer and closer to the center or where the potential is the highest, you're going to get that gradient slope going up. And so next, we are going to define potential as a gradient of the electric field. Okay, so now let's take a look at the electric field of a dipole and how we can represent those equipotential lines. So we know what the equipotential lines will look like for each individual point charge. So for a negative point charge and for a positive point charge, we know that as we get closer and closer to the center, the equipotential line should get closer and closer because the magnitude of the electric field will increase. So that makes sense. And so as we go out, they should be spread farther apart. But because there are now two charges together, we know that there should be some sort of differences in terms of how we represent the equipotential lines. So as you can see over here, there's a shift as you get farther and farther away from the center. For the negative charge, it goes towards the left. For the positive charge, it goes towards the right. And in the center, there's an equipotential line that's just straight, almost like a barrier between the two of them. So that means that from the bottom part here to the top part here, the electric field lines go out from the positive charge and into the negative charge. For each of these lines, there is symmetry between the two of them, and there is a potential of 0 over here. So that does make sense. Now outside, you have equipotential lines where, because these two charges are closer together, you're going to have a slight push where the equipotential lines will be pushed outwards. So there's a shift towards the left over here and a shift towards the right over here, because here you have electric field lines going out and then creating a larger loop around the whole charge distribution, whereas over here they actually go out and come in. So over here you have a less strong and a weaker electric field and a weaker potential. So that's why these are spaced out a little bit more. Now, looking at the next one, we have the electric field of two equal charges. And something to keep in mind is equipotential lines can never cross if they are of different potentials. Can they cross? Yes, they can, because over here, it is crossing, or maybe they're just touching. But what we can assume is that if they do look like they're crossing, the equipotential lines for the ones that cross, they have to be at the same potential. So what we can guarantee here is that the equipotential line here and here, they're all at the same potential because they're touching each other. Now, if I have this one over here, it cannot cross. So only one of these can cross, and we take the equipotential that's continuous and have that go through the entire loop. So we have now two positive charges or two equal charges, and the main difference really is there is no more barrier in the center because the electric field lines do not come out one and into another, they repel. So the electric field lines are going to repel going up, which means that at any point along any of these electric field lines, there will be a point of equal potential. So going here, there's a point of equal potential here, here, and here after the electric field lines are repelled and go up, and same down here. So you get a fairly different shape of an equipotential line where you kind of encompass the whole thing as just a larger or more oval shaped charge, it almost seems like, where you have the equipotential lines radiating out farther and farther in an oval shape. Now, what are some important trends for equipotentials? Number one, if you take a look at the examples from before, we know that equipotential surfaces and lines and electric field lines seem to be related. So if I go back, if you zoom into each of these, you'll notice that the equipotential lines are perpendicular to the electric field lines. So that means that's something that we can notice as an important trend. They are perpendicular to each other. That's one characteristic of equipotential lines. Next, we also notice that the farther the equipotential lines are spaced apart, the weaker the electric field. And the closer they are, the stronger the electric field. So these are the important trends for equipotentials to know moving forward. Next, we have the potential gradient. If we have electric field lines, that means we can get equipotentials. Once we have equipotentials, it means that we can take a look at gradients, similar to how we have those contour maps, as you've learned probably in Calculus 2 with gradients, or maybe Calculus 3. So let's consider the potential difference dV between two nearby points separated by dx in the x direction. Essentially, now you have 2 points over here. We can say that the change in potential between two spots on the x-axis, so dx, dv is equal to negative ex dx. And if we have that, we can actually define the electric field as the gradient of your potential. So that means it's negative dv over dx in the x direction, and then in the y direction, and then in the z direction. So these three represent the potential gradient definition of an electric field. So now, summing up everything, we have three ways of calculating the electric field: from first principles, from Gauss's law, and from the potential gradient. So now we have three different options of calculating the electric field, and we have to choose which one is easier for us in different scenarios. Now let's take a look at the potential of a charged disk, version 2. We're going to see if there's an easier way to do this with some of the new knowledge we've learned. So a charged disk of radius A carries a charge Q distributed uniformly over its surface. In problem 6, we found the potential at point P on the disk's axis at distance x from the disk. Now we're going to use that result to find the electric field on the axis of a charged disk. So basically, what we're trying to do is see if there's an easier way for us to determine the electric field if we already know the potential. So it says pick an axis. Since we already have, since the disk is on the x-axis, let's choose the x-axis for our problem. So we know from problem 6 that the solution we found was 2kq over a squared, and on the x-axis we have the square root of x squared minus a squared plus a squared minus the absolute value of x. So that was the solution. Now, what if we want to find the electric field? We're just going to scroll down over here. We may want to use the gradient. So E is equal to negative del V, and that is going to be equal to negative di V over di X. It's the same for each one. It's the partial derivative of each of these. Where ijk is simply the unit vector in the x, y, and z directions respectively. We know that the y and the z components will essentially cancel each other out. So all we have to worry about would be this one. So Ex is equal to negative di V over di X in the x hat direction, since we're more used to that. Scroll down. So I'm just going to quickly point out that these cancel each other out. So we can just ignore them. Now this is then going to be negative derivative of, we have 2kq over a squared x squared plus a squared minus the integral of x. And if we want to derive it, we end up with minus 2kq over a squared being the constant. And then we should get 1 over 2x over the square root of x squared plus a squared minus plus 1. So why is that? We had to use a substitution chain rule. U equals to x squared plus a squared. Du is equal to 2x dx. So d over du of the square root of u is equal to 1/2 u of negative 1/2 dotted, or not dotted, times 2x. So that's where that came from. So this means we end up with 2kq over a squared, and this is Ex. We have plus or minus 1 minus x over the square root of x squared plus a squared. So that is another way to solve for the electric field, and it's going to be in the r hat direction. Oh, sorry, not r hat direction, x hat direction. So that would be how you would approach solving the electric field in a different manner using the potential gradient. Now, we haven't taken a look at conductors yet. That will be for the next chapter. But any conducting material in electrostatic equilibrium will not have an electric field within it. So I don't want to discuss too much about conductors. The only thing I wanted to talk about regarding conductors is the fact that if you do have a conductor, which is an object that has charge flowing freely through it, all of the charge is just going to go to the surface and be distributed evenly across the surface. And because the charge is distributed evenly across the surface, you have electric field lines going out for a positive charge and in for a negative charge. And what's unique is that if you have all of your charge located on the surface and it's evenly distributed, you can break up the surface into many tiny dqs that act as a point charge. And that means that the electric field line will be perpendicular to the surface. And so the actual surface itself is an equipotential line. So that is a unique feature of a charged conductor, where you have a charge on the surface, and if you break it up into tiny little pieces, each of them will radiate out or in an electric field line that's perpendicular to the surface. And by that definition, the surface itself is an equipotential line, and that surface is going to, but the shape of the surface will define what shape your equipotential line has. So for example, this has a kind of like an egg-shaped surface. So as the electric field lines radiate out from the positively charged surface, you have an egg-shaped equipotential line getting spaced out farther and farther apart as you go through it. And of course, if you have a higher curved area or an area of more curvature, that's where you have a stronger electric field because there's more charges kind of allocated within that area. Next, I want to take a look at equipotentials on two conductors. Once again, we haven't talked about conductors a lot yet, but we now have a positively charged object where the charge, because it's a conductor, is just allocated on the or distributed on the surface. You then have a negatively charged plate where the negative charges are distributed across the surface as well. But the thing is, if you put the two together, there are positive charges and negative charges, and they're going to want to come closer together. So then you get this uneven spacing and distribution of charges where the negative charges are going to go towards the middle a little bit more to get closer to the positive charge. And you end up with this electric field distribution and equipotential lines that are shifted towards the left because of the rearrangement of those electrons. So what is the difference between an equipotential and a Gaussian surface? We only use Gaussian surfaces for Gauss's law, and we get to choose a convenient surface, whereas we can't do that with an equipotential surface. It actually depends on the shape of the charge distribution, and we have no choice with that. So sharper curves in a conductor shape will represent stronger fields, and that's because the charge density is higher in that area of higher curvature. So next, we're going to go through a few practice problems that discuss conducting spheres and how we can approach those problems to determine the potential difference. So problem 9 has to do with two conducting spheres. We haven't really talked about spheres. We haven't really talked about conductors yet, but I do just want to go through some of the problems very briefly based on what we already know. And so it will all be about potential. I have 4 slides dedicated to solving this problem. We do not need that many slides, and we don't need that much space. The problems are fairly straightforward. Step A, B, C, D really refer to just parts A, B, C, D of the problem. So here we have two conducting spheres that are each 5 centimeters in diameter, and each carries 0.12 microcoulombs of charge. They're 8 meters apart. I should probably draw the diagram first. So I have this being my first sphere, 2.5 centimeters because they're 5 centimeters in diameter. They're both the same, so let's just draw 2 identical ones. And they're 8 meters apart. Wow, they both have a charge Q1, Q2, and the distance between them is 8 meters. Okay. Now in part A, it's asking us to determine the potential on each sphere. So V is equal to KQ over R, which is equal to 9 times 10 to the 9 Newton meters squared per coulomb squared. The charge is 1.2 times 10 to the negative 7 coulombs divided by R, which is 0.025 meters, because we can't use centimeters, and that is going to be equal to 43.2 kilovolts. So that is the answer for that one. Both spheres are the same, so the potential on each sphere will be the same. Part B, we're trying to find the electrical surface at the surface, electrical field at the surface of each sphere. So E is simply going to be equal to kq over r squared. And the reason why I'm doing this question like this is because we know v is equal to kq over r. We know E is kq over r squared. So essentially, this can be v over r, and we simply have 43.2 kilovolts divided by 0.025 meters, which is equal to 1.73 times 10 to the 6 volts per meter. And that's our answer for B. Now C is asking us, what is the potential halfway between the spheres? So halfway between the spheres, we are going to have to use superposition because there's the effect of the two spheres. B total is equal to KQ1 divided by R1 plus KQ2 divided by R2 equals, and now remember Q1 is equal to Q2, so let's just use Q. R1 is also equal to R2, so we can just use R. So we have 2 KQ over R, which is equal to 2, 9 times 10 to the 9 Newton meter squared per Coulomb squared. Q is 0.12 times 10 to the negative 6 coulombs, divided by R, which is going to be 4.0 meters because it's supposed to be halfway between the two of them. And that is equal to 540 volts. Now part D, also fairly straightforward. We want to calculate the potential difference between the two spheres. Well, we know V1 is equal to V2. So that means delta V is equal to V2 minus V1, which is equal to 0 volts. So that is going to be our potential difference of 0 between the two of them because they're equipotentials. So just to double check, step B, C, and D are just extra space, extra pages for you to show your work and to write out some notes, but we definitely do not need that much space for this question. This last problem we want to go through has to do with a conducting sphere and a shell. So a conducting sphere, 5 centimeters in radius, carries 60 nanocoulombs of charge. It's surrounded by a concentric spherical conducting shell of radius 15 centimeters, carrying negative 60 nanocoulombs of charge. Find the potential at the sphere's surface, taking the 0 of potential at infinity. Okay, so in this case, we do need a diagram, just so that we know what we're talking about. We have a solid conducting sphere that's 5 centimeters in radius. And then you have a shell. It is a conducting shell. It is 15 centimeters in radius, carrying. So this arrow just simply means how much charge there is on the surface. It has minus 60 nanocoulombs of charge. Just remember, for a conductor, all of the charge is on the surface. So then over here, we have 60 nanocoulombs of charge on the surface. We're going to call this surface A, and we're going to call this surface B. Now we want to find the potential at the sphere's surface. So we want point P over here. So first we're going to have to find the equation for the potential of the inner sphere. So the electric field outside any symmetrical charge distribution is that of a point charge with a total charge of Q. So from infinity to the sphere, we can have E equals to KQ over R squared. We know that RA, we'll just do R infinity for that point, is equal to infinity. And then we have RA being equal to 0.05 meters for the 5 centimeter mark. The potential of the sphere is going to be from infinity to 0.05 of E dotted with dr. Or we have from infinity to 0.05 kq over r squared dr. Now keep in mind that when we're taking a look at potential and we're going from infinity, so I'm just going to draw, let's see, purple. So I'm going out from infinity. I'm going to be reaching RB first, and then I'm going to be reaching RA. So that means from infinity to RA, I have to break up my calculation from infinity to RB, and then from RB to RA. So this means I have the integral from 0.05 to 0.15. Oops. So keep in mind I've taken out the negative sign, so I'm flipping it around. We have KQ 1 over R1 or R2 R squared dr plus the integral from 0.15 to infinity of k and then q1 plus q2 divided by r squared dr. So V sphere is going to be equal to kq1. We have the integral from 0.05 to 0.15 of dr over r squared. And then we have q1 plus q2 of the integral from 0.15 to infinity of dr over r squared. So now we do have to take a look and solve for the potential. We know that over here, q1 is equal to q2, so total is 0. So that means this whole thing can just be 0 valued. Now the only thing left is just the first component, which we're going to solve for on the next page. So V sphere is equal to k q1. I'm going to solve for this, which is -1 over r from 0.05 to 0.15 plus 0. And then you end up with kq1 1 over 0.05 minus 1 over 0.15, which is equal to, let's do 9 times 10 to the 9 Newton meters squared per coulomb squared for K. Q1 is 60 times 10 to the -9 coulombs. Then you have this relationship. And your final answer should be 7,200 volts. And that would be your final answer for this. Now, when you're taking a look at solving for potential, for different charge distributions, there are various ways of doing it. This is just one way. As things get more complex, especially if you have conducting shells within shells within shells, for example, then you will have to do multiple calculations back to back. Because you have to split up the potential from infinity to the point you're looking at based on how many shells you have and how much charge it encompasses.